So James is going to talk to us about how we use existing infrastructure for the purpose of consuming hydrogen. Over to you, James.
Okay, can you all hear me?
Loud and clear. That's fantastic.
Loud and clear, fabulous. As the last speaker, I hope everybody's had their coffee in the morning in Glasgow and it's kicked in. So my name is James Holbeach. I'm the Global Director for Energy Transition and Flow Assurance within Wood, within our Applied Intelligence Group. I'm just going to start off by quickly correcting Dan. He did mention that I'm from Brisbane. I'm not. I'm actually based in Perth. That's some 3,621 kilometres away.
Sorry, James.
To put that in context, if I was to fly from Glasgow via Milan in a straight line, I'd end up somewhere in northern Libya. So there you go. So look, I'm going to start off today on a little bit of an odd note. There is currently a computer game under development, and it's called Star Citizen. It's a massive universe-scale virtual environment, and the technology to run it on home computers cheaply actually does not yet exist. Yet it's being developed, and it's being developed based on proven technologies to meet a demand that will exist in the future. And in the process, it's accelerating the pace of graphics, of MMOG development faster than ever before. Here at Wood and within our group, we're also helping our clients prepare for the networks of tomorrow. And while many of our hydrogen-enriched natural gas customers are still in the very early stages, examining commercials, I guess, and the initial engineering and concepts, some are a little bit further progressed, and some of the new technical challenges that you might not have heard of are beginning to pop up. And a little bit like Star Citizen, within our group within Wood, we're developing some unique tools and some unique, I guess, workflows to address those challenges of tomorrow, but based upon solid and proven technologies of the past. And that's what I'm going to talk about today. To use a Grace Hopper quote, I'm actually more interested in the future than I am in the past. So within the hydrogen space, Wood has a three-pronged approach to the value chain of making it, moving it, and using it. You know, Omar started off this session with a fabulous presentation on opportunities of making hydrogen using blue hydrogen technology, SMRs, and also bioreforming, and also Beth, I love your name because my daughter's name is Beth as well, talked about also other issues in terms of making hydrogen and separation of those CO2, and also using the hydrogen and using it in different locations and separation of that hydrogen from natural gas streams. And then Colin talked a little bit about moving it and the different vectors of moving it, and there are a lot of different vectors as well. One interesting little tidbit, in fact, is that liquefied hydrogen has less hydrogen per unit volume than metal hydrides. So metal hydrides are where you absorb the hydrogen into a metal lattice, and liquefied hydrogen has less hydrogen density than metal hydrides. That one does my head in. But anyway, so today's presentation, what I'm going to talk about though is moving it. In particular, the very narrow focus of moving hydrogen using existing gas infrastructure. That is, using existing gas transmission and distribution networks to transport hydrogen from source of hydrogen, from whatever color of hydrogen you may have, to industrial and domestic users. Now, this is very attractive to a lot of the world's midstream companies because they have a large asset base and sunk cost base in their infrastructure. And Colin mentioned the fact that there's a lot of steel in the ground, and it would be great if it could be used to transport green energy or greener energies to users around the world. It would accelerate rapidly the adoption of decarbonising technologies. However, as simple as this looks on paper in my very basic diagram here, there are some engineering challenges associated with hydrogen enriched natural gas, or HENG. The first and probably the most common one that most people are aware of is the integrity and material selection challenges. And Colin has spoken about that at some length about, you know, what kinds of materials can cope with what kinds of concentrations of hydrogen in what partial pressures and what temperature scenarios. This is a really key step. If you can't put hydrogen in your system and guarantee the integrity of the system, then you're not about to do it. Safety is also a very big concern for hydrogen, in particular around things like fugitive emissions, which again Colin touched on. And for your information, there have been some studies which show that the fugitive emissions of hydrogen from pipeline networks are 2 to 3 times higher than those for natural gas networks. However, it also disperses a lot more quickly because it's a lot lighter. That said, hydrogen has a much larger explosion limit between its explosibility limits, and it's also got a much higher flame velocity. So there are a lot of different issues with hydrogen and safety in terms of stratification and enclosed spaces which need to be addressed. And those things are being talked about a lot, and most people who are familiar with the hydrogen space should be aware of them. However, the other engineering challenges probably are not as well known. There are engineering challenges around the fluid properties. And so that's going to affect, and these are the fluid properties, some of the fundamental fluid properties, the densities of natural gas, the speed of sound, etc. These are going to affect things like flow metering and also process design and operations and flexibility around operations of natural gas networks. And it's those last two that I'm really going to focus on in this presentation. So I know this is a busy slide and I know you're looking at a very small screen, so you're not going to be able to read it. But for I guess the point of explanation, the development path of hydrogen enriched natural gas is one from simple to complex, and it's pretty common development path. You start with something simple, and as you get more confident and mature, you get to more complex networks. So generally, hydrogen enriched natural gas operators will look at commercial feasibility assessments. If they figure they can make some money from it, they'll look at some desktop engineering assessments. Can we put hydrogen into our network, into our existing infrastructure without damaging it? If the tick is yes, then they'll probably look to some small pilot scale field trials, normally at low pressure, and they might even then move into some variations in the hydrogen content they're injecting. And then over time, they get more and more complex into medium and high pressure transmission systems, which have higher complexities with multiple different users, perhaps multiple different sources, and then eventually to a point where you have integrated control of the network based on users and sources. Now, most of the players out there in the market at the moment are very much at that early phase in the pilot scale, in the small scale, low pressure environment. But most of the engineering challenges in terms of safety and integrity and materials occur throughout that entire thing. They start from the very start. But the reason why we've not heard as much about some of the material and fluid properties, the fluid property challenges, is because they don't really become an issue until a little bit later on. Now, there are some operators out there who are talking about some more complex systems, and that is why we are working with those operators to develop solutions to. And same with operability. Operability engineering issues also really come into their fore when we get more complex systems. So I'm going to focus on the fluid and the operability issues in a little bit more detail. So fluid properties. Fluid properties, and when I say fluids, a gas is a fluid, a liquid is a fluid. It's just an engineering parlance for those who are not engineers. Fluid properties are critical inputs to pipeline design, to material selection operations, capacity assessments, process engineering, and metering and allocation. An accurate prediction of fluid properties are essential for robust engineering and operations. There's an old saying, rubbish in equals rubbish out. If we don't get the inputs right to start with, we get crap out at the end. And fluid properties are the primary input into most process engineering studies. So I like to often use this photograph I took at my place just outside of Perth, and it shows the Milky Way. It shows the second, third, and fourth closest stars to the Earth That's Proxima Centauri and Alpha Centauri A and B in the Milky Way. Those three stars, like the closest star, our sun, are boiling fusion reactions of mainly hydrogen. Every red nebula you can see in this photograph is the Balmer decay of hydrogen alpha. And hydrogen is by far and away the most common observable element in the universe. In fact, it accounts for something like 75% of all baryonic matter. So because it is so common, we know a lot about it. We know its properties, we know its fluid properties, we know the way in which it behaves. We know that when we liquefy hydrogen, we become, there are some quantum mechanical issues which need to be considered. There are spin isomer states of liquefied hydrogen of author and para, and if you don't get them right, you will get huge amounts of extra boil-off gas. Really weird stuff, but we know it well. Unfortunately, gas is not hydrogen, and it's not simple, it's a mixture. And therefore, because it's a mixture and it's variable, it's very hard to understand how a mixture of different fluids behaves. And so what we do in engineering is we use models, and what the models are called equations of state, based on the composition, the pressure, and the temperature to predict the properties of the fluid that we're modeling. One of Wood's subject matter experts in this space, Dr. Dale Erickson, said once that hydrogen is like the energetic kid. It's small, but it interacts with everything, which makes it hard to predict. It is a very small molecule. However, its kinematic diameter is about 120 picometers, and I know that means a lot to most of you. It doesn't, but that's actually quite large. It's actually of a comparable size to other molecules, despite the small physical size of it. And that's important because it means that it's very energetic, it bounces around a bit, but it interacts with other molecules in a mixture extensively. And this makes it very hard to predict physical properties. And those fluid properties like density, like specific heat, like enthalpy, like Joule-Thomson coefficients, etc., are critically important for metering. They're critically important for line sizing and capacity assessments, hydraulics, and dew pointing. And so if we get them wrong, then we get all of those things wrong. And to put that in context, about a 0.5% error in capacity because we got our fluid properties wrong for a pipeline like Nord Stream would result in a loss of about $50 million plus per year. These are not unusual numbers, and they're common numbers across the industry. The problem is hydrogen has a really, really big impact on the thermophysical properties of natural gas. And to predict those thermophysical properties, we use equations of state, and the standard equations of state are not necessarily suitable for hydrogen systems. AGA8 is the standard equation of state. GERG 2008, which is a multi-parameter equation of state, is likely to be more accurate. And I've shown on the plots down the bottom a couple of the ways in which some properties, like for example, the speed of sound, is impacted by the presence of hydrogen, and it's a significant impact. So we within intelligent operations are, and within Wood are undertaking research to in these spaces to better define those equations of state, and also develop tools and technology to ensure that we can accurately predict hydrogen-enriched natural gas fluid properties. But there are also some operational challenges with hydrogen-enriched natural gas. So if you consider a gas network, and it's a simple gas network, you have one source of natural gas going into the network, then it's very easy to predict what's happening in that network. You've got the same composition at all locations in the network because you have one source. It might be going to different users, but you don't care. Yeah. Multiple sources of natural gas going into the network, even if they have slightly different compositions, which is common. Yeah. Again, you have a pretty confidence in understanding what the overall fluid properties are anywhere in the system, because the slight variations in composition of natural gas don't have a huge impact on the fluid properties. And so therefore we can do engineering on this in a pretty straightforward way, and we can understand the operation of this in a pretty straightforward way. We don't need to know what the composition is at every single point in the pipeline. during operations because it doesn't really matter. Inject hydrogen, however. If we inject hydrogen into different parts of the grid, and we're injecting hydrogen at different concentrations into different parts of the grid, and the hydrogen has a big impact on the fluid properties at wherever location it is, then we need to know what the composition is at every single point in the grid. Unfortunately, we don't. We need to be able to model this or be able to measure it on a real-time basis. This is a fundamental difference to the way in which natural gas grids are currently operated and designed. It starts to begs a whole pile of operational questions. What happens if the natural gas at a location shuts down, but the hydrogen doesn't? What happens if the hydrogen shuts down, but the natural gas doesn't? What happens if one of the users changes and therefore the gas is distributed in a different way? And what happens if the network has some ullage or the response time of a network to a change is wrong? Does it mean we need to inject 10% or whatever fixed concentration of natural gas into the network at all locations to ensure stability? And if that's the case, what happens if the hydrogen drops out at that location? Does that mean you just don't inject natural gas? So these are lots of operational questions which raise operational complexity, which are not currently seen in existing midstream infrastructure. When we look at solving fluid property and operational issues like this, this is flow assurance. This is exactly the same thing, ensuring the flow and productivity of gas from one or hydrocarbons or energy from one location to another. When we looked at this for hydrogen, we realized that there is no available design tool which could give us the required level of accuracy and physics for hydrogen-enriched natural gas. We needed something that was vendor independent, that could work in operations and design, but for any control system. We needed something that was transient, compositional, fast. It was high accuracy equations of state and had full physics, including thermodynamics. It was scalable from small to very large networks. It was field proven, because if you're going to use something to design a network, you want to be able to trust it. And ideally, this is a bit of a nice to have, but it's also a one-stop shop, so that you could use it for your upstream system, your multi-phase system, as well as your single-phase system. And so we couldn't find anything out there in the marketplace which ticked all of those boxes, but we did find a product which was pretty close, and that is Wood's actual internal and unique special flow assurance tool called Virtuoso. So Virtuoso is exactly the description I gave before, but up until just recently, not hydrogen. It is a multi-phase, natively multi-phase transient thermodynamic process simulator for design and operations. It currently runs around 10% of the world's gas supply in a real-time operational sense. So it's taking real-time field data and then providing feedback to operators in real time. It's used for both design and operations. We're actually using it currently for a number of hydrogen-enriched natural gas projects around the world because there was no other product, and this was the best. But it's also used globally in operations, and in fact, it's used in about 30% of all upstream all upstream LNG supply is operated using Virtuoso as an operator assistance. In gas systems, it's used for inventory management, blending management, integrity management, leak detection, which Colin mentioned before, and leak detection systems, as well as operations. Just to kind of round out what it is, because I'm going to show and demonstrate some of the challenges with hydrogen by using Virtuoso, but I just want you to understand that this is not new technology. All we've done is we've taken an existing technology and slightly modified it to allow it to be able to accurately model hydrogen as well, and hydrogen blended natural gas. Virtuoso was used in the UK national grid for blending, upstream blending management system in the Teesside area. It's used for 30% of Europe's natural gas supply through Nord Stream 1 and 2, And in fact, it is one of the primary operational tools for that. The entirety of Israel, both upstream and downstream, and also on Gorgon and Wheatstone, huge mega gas projects in Australia, and also the carbon dioxide capture part of that project is now using Virtuoso to help it manage the challenges that it had before. And we're very proud of that. So that's enough of me talking about what it is. Let's have a look at what it does. So what I've got here is a fictional world called Cavendish. And I'm hoping you can see my screen, but this is the gas distribution network on Cavendish. It's actually broadly based upon a real world gas distribution network. And this is a Virtuoso model. And so what we're going to do, this is, I'm running a simulation here. It has been accelerated for the purposes of the display because I don't have the full time. The time counter here shows the number of hours of real time that we've modeled. So we've modeled 10 hours of real time. The graph is showing the flow rate at this point in this pipeline and the hydrogen content at this point in this pipeline, as well as the flow rate of this user down here is shown by the blue line. And I appreciate that it's very small and you're looking at a small screen, so I'll try and talk through to you. So we've got a number of sources throughout the network. We've also got a number of users. As I said, this is based on a real world scenario. I'm just going to come back a little bit. At some point, this user down here, down the bottom, is going to stop taking gas. For whatever reason, the user tripped. And so you see the flow rate it's taking suddenly drop. It takes a little bit of time for the flow rate going into the pipeline to drop as well. And that's normal. This is a very large pressure balanced gas distribution network. There will be gas going in different directions. The total distance from one end to the other is around 400 to 500 kilometers. And that's a lot of inventory and a lot of pressure that swings and fluctuates. The compressor is changing in terms of its speed and its fuel gas usage as well throughout the network. But at some point, this user is going to start saying, I'm ready to take gas again. There you go, it started taking gas again. Again, you'll see the network responds quite smoothly. It's taking natural gas back again out of the network in a very smooth manner. This is how natural gas networks naturally operate. Yep. They operate on a pressure balanced system, pretty simple. They don't care what the composition is at any point. We run these scenarios to make sure we don't ever depressurize the system too much or overpressurize the system. However, it's all nice and smooth. Okay. So I bet you can guess what I'm going to do next. Let's inject some hydrogen into this network. Okay, so this is again the same simulation. Now, the thing about hydrogen when we inject hydrogen is that it's got a much lower volumetric density compared to natural gas. That means to meet the same energy content, you need to inject a hell of a lot more volume than natural gas. So what that means is you will pressurize the system. You'll begin to pack the system up, yeah, and you'll start to see that change happen. So in this first example, all we are going to do is we are going to start injecting some hydrogen at this source up the top, Hartek gas plant. That's the only change. We are just going to change the concentration of the stuff going into the grid. So you should be able to see the hydrogen now being transported in the grid. The different colors show the concentration of hydrogen at all locations in the grid. You can see that the graph is beginning to show some variation in the hydrogen content and also some variation in the flow rate going into the pipeline at this point. Okay. Now this is normal. Now the reason why you're seeing variation in the hydrogen content is because this is a pressure balanced network. We're injecting hydrogen here, but we're blending it with extra natural gas from here, or potentially extra natural gas from here. And it pressure balances across the network. It's a very complex interplay between hydraulics and flow rates. But it comes to somewhat of a steady state. You'll also see some changes to the compressor curves because compressors use hydrogen as a fuel gas source for the compressor. Now, when the compressor uses hydrogen as a fuel gas source, when the hydrogen comes in, it obviously means that the compressor needs more hydrogen. And rotating equipment doesn't like rapid changes in composition or rapid changes in energy content. And so when we run these scenarios, we're looking at how those changes happen as well. So now we're going to do exactly the same thing we did before. We're going to say this user down here stops taking gas. What happens? If you think about what will happen here, if this user stops taking gas, the system will begin to pressurize, but you start seeing more hydrogen being injected into the system and less natural gas potentially being blended into it. Or maybe you're going to see more natural gas blended into it and less hydrogen. So this user stops taking stop taking gas now. And if we watch, you'll see that the hydrogen content, while the flow rate into the pipeline begins to drop, the hydrogen content begins to swing. Yep. It begins to change quite rapidly. And that's because the system has become unstable. It's become chaotic. Yeah? And this is this is not good for most industrial users. Most domestic users can cope with this kind of variation, but industrial users do not like this kind of variation in composition and energy content of the pipeline. So again, I'll skip forward a little bit because I know we're running a little bit late. If we look at the the WABI over time, it all stays within gas quality issues. However, the rate of change of some of these things may go outside of those quality constraints. And currently, gas quality specifications of systems don't account for this, and they don't state that you can't change things too rapidly, and that may have to change in time. So there are elements of the industry and elements of the gas industry who have been doing this stuff for years. They've been operating their systems in very standard ways, in very standard pseudo steady state methods, using Excel spreadsheets and standard modeling tools for running their system. Hydrogen means they can no longer do that. Grace Hopper, who was a rear admiral for the US Navy and also a very famous computer scientist, once said that the most dangerous phrase in the language is that we've always done it this way. With hydrogen-enriched natural gas, we can't do it this way anymore. It's going to have to change. That's all I've got. That's where I'll leave it up. I'll leave you with one final quote from George Bernard Shaw: "Progress is impossible without change." The gas distribution industry will have to change for hydrogen, and I hope that they're ready. That's all I've got. Thank you.
Thank you very much, James. We're running a bit short of time before the next session, but I don't know if anybody got any questions they want to direct towards James.
I can hear from you. I'll speak up. Hi, James. It's Rob Helm here.
I can see you, Rob, and I can hear you.
Good. Just on the compression side of things, we haven't talked much about the mechanical equipment, maybe to Colin as well. Is there much difference or impact on the pumping power or the mechanical equipment that we have to consider for these networks at the same time?
Yeah, it's a really good question. Yes, there is. So the compression equipment is likely to have to change slightly. There are different compressibilities of hydrogen versus natural gas. Hydrogen is a little bit better it's a little bit easier to compress than natural gas, and so that helps. But on the flip side, you're going to have more of it. You're going to have a higher volume of it to compress. There are also issues in terms of fluid properties around Joule-Thomson coefficients, the CP over CV, which actually drives, for example, compressor after duty efficiencies, etc. Sorry, compressor after cooler duties and their efficiencies. So yes, there will be changes. Whether they're material in the short term for smaller scale systems, that's unlikely. But for larger scale networks, absolutely. Yeah. Some of the big compressors are really, they operate on a knife's edge. And so therefore, there will be issues and things that will have to change.
Thanks, James. Anything else? No? Okay, we'll wrap up there. And I think, from what we've shown you this morning, we see hydrogen as a key tool to meet net zero challenges in both industry, domestic applications and transport. There are a number of challenges to its generation, its transportation and its use, but the solutions and tools to address those challenges are developing or in place today. And I think, as Beth said earlier, we really need to start making this happen now.